Hey there, everybody. We're going to talk about the magnetic field that's inside a device called a toroid, and then a related device called a solenoid. And solenoids are really important devices. You see them have lots and lots of applications, so it's a pretty important topic. So to find the magnetic field of a toroid and a solenoid, we're going to use Ampere's law. So let's review Ampere's law. Now, Ampere's law is written this way. B dot ds equals mu naught I enclosed. Now, it's really important that you understand what all the parts of this mean. I mean, this is one that you should memorize. This is one of the big equations in all of physics, and it expresses a very important idea. It really is a shortcut way of looking at what is the source of magnetic fields. I mean, what causes magnetic fields? Well, current does. And so what this does is it gives us a simple way of figuring out what the magnetic field is for very highly symmetric currents. And so we're going to be using this to find the magnetic field due to a toroid and a solenoid. Well, what is a toroid? Well, a toroid is basically a donut. Okay, so here's a toroid. Okay, and so imagine you have some kind of shape like this. Looks like a donut. Okay, and then what we're going to do is we're going to wrap a wire around this donut in this way. And I'm going to kind of draw it like this. Let's imagine that the current comes in like this, and then it goes boom, and then it goes back behind, and it goes boom, and then it comes behind it, and then like this. And now I'm not drawing as many loops as there would actually be probably in a real toroid, but I don't want to draw, you know, hundreds of loops because it would take too long. But I think you can imagine this kind of a shape where you're taking wires and you're wrapping it around this donut. Okay, and if you use Ampere's law, you're going to get a result that I don't know if you really can solve this using the Biot-Savart law. But Ampere's law lets us do it fairly easily. Because what I want to know is what is the magnetic field inside this loop, and what is the magnetic field outside? So here's my current, I. It's a steady current, and it goes in, and then it goes into the paper, and then out, in, and then out again with each turn of wire. When you do a complete loop around, we call that a turn of wire. Okay. Well, we're simply going to use B dot ds right here to figure out what the magnetic field is. We're going to use Ampere's law. Well, let's make that the center, and let's look at what the magnetic field is right in there on the inside. Well, we go B dot ds, and here's each one of those little dashes represents a ds. Okay, and so equals mu naught times I enclosed. Now B is just whatever the magnetic field is right there. And then what is ds? Well, when I sum all the ds's, I get 2 pi r. equals mu naught. Now, how much current is enclosed by this loop? What is the enclosed current? It's 0. Now, R is not 0, so that means that B has to be 0. Therefore, B equals 0 inside here. There is no magnetic field due to these currents in the donut hole. Now, what about out here? What would the magnetic field be like right there? Well, what I'm going to do to get this part, here's my Amperian loop. I'm going to look at a cross-section of this. Okay, so here's my Amperian loop, like this. And then if I look right in here, look at this wire. Boom, do you see right there? The current is going into the paper. So I'll represent that as a little end of the paper, into the paper, into the paper, into the, each one of these wires, into the paper, 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 into the paper. Now when you're out here, you've got out of the paper, out of the paper, out of the paper, out of the paper, blah, 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 blah. But we don't really care about those because this is my Amperian loop. And so what Ampere's law says is that if I say, okay, B dot ds is equal to mu naught times I enclosed. Okay, well, I'm going to say, well, B is just whatever B is, and my ds's, what are those? Well, that's 2 pi r. When I sum them all up, right, it's the circumference of a circle, and then this is mu naught. Now, how much current is enclosed by this loop? Ooh, well, we've got I on each wire, but I've got 1, 2, 3, 4, 5, 6, 7, 8. Well, however many loops there are. Now, we're going to say that there are n turns of wire. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I really drew 10 loops of wire, so I could put 10 right there. What we're going to do is we're going to say, hey, take this current and multiply it by the number of turns of wire, which would be 10, except I'm going to do it in general. So let's say I have n loops of wire. Now I can solve for the magnetic field inside the toroid. Okay? And if I do that, I say I've got mu naught I. Well, let's put n. It's traditional to put the mu naught n times I over 2 pi, and then I'll just put the 1 over r out here, because this is all constant stuff. And so the magnetic field varies by 1 over r. This is our answer. This is the magnetic field inside a toroid. And what if you're outside the toroid? What if your R is out here? Well, I'm going to draw my Amperian loop around like this. So let's draw it again out here. So let's take my Amperian loop. Okay. Now if I look on the inside here, I've got a current in, 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 current in. But if I go on the outside, for every current in, I've got a current out, 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 current out. And so when I do my B dot ds, again, equals mu naught times I enclosed. Okay, this is B, this is 2 pi r, this is mu naught. But notice that how much current is actually going through this loop. Well, you've got currents going in, but over here you've got currents out. And when you add it all up, you've got 0 current through the area created by my Amperian loop. And so B equals 0. Now what this means is that if you have a toroid, if you take a donut and you wrap wire around it and you have a current going through it, current creates magnetic fields. But it's not creating any magnetic field outside the toroid, either in here, in the donut hole, or outside the donut. There's no magnetic flux. It's all concentrated inside the toroid. And when you do an experiment, when you actually make one of these and you turn it on, you put a current in there, there is no measurable magnetic field out here if it's a really good one. Now, what's the direction of the magnetic field? Well, this takes a little imagination. Let me zoom in. Let's take a look. Look at this wire right here. It's creating a magnetic field around itself, right? And it's going in. So if I use the right hand, oh, I should zoom out. It's creating a magnetic field around itself that looks like that. Looks like that. Looks like that. Okay? So when you're out here, these magnetic field lines, notice that when you're between two wires like this, you've got a magnetic field going down, but on this one you have one going up. So these two magnetic fields that are in between these wires, they tend to cancel each other out. Whereas up here, they tend to reinforce each other. They reinforce each other. They reinforce. So what happens is that you've got a line of magnetic field that looks like that. So really what's happening in the toroid, if you draw the magnetic field, it looks like that. Now, by the way, if you look at the magnetic field line coming out, like if I take a look at this wire right here, and then I'm going to draw it right there as a current coming out of the paper. Well, if I draw a magnetic field line, it goes like this, right? So it goes like that. And so notice that on the inside of the toroid, it reinforces the magnetic field. Here's the one next to it, right? So it does the same thing. In between the wires, they cancel each other out, but inside the wires, you get a magnetic field line that tends to reinforce itself like that. So what happens is that on the inside here, you've got lots of magnetic field lines that are, and here's the magnitude of that magnetic field. It's that's inside that toroid. It's mu naught times n times I over 2 pi, and n times 1 over r. So this is the equation, and that's the direction. One way you can figure out the direction is there is a right-hand rule for toroids and solenoids, and that is, well, you could do it by grabbing a wire. Let's take a look at this wire right here. See this wire going over the top? Grab the wire with your right hand and let your thumb go in the direction of the current, and notice that on the inside of your toroid, your fingers are pointed that way, which means the magnetic field is going to circulate like that. Another way of doing it is let your fingers be the currents and let your thumb represent the magnetic field. And if you grab it the way that the wires are curling around the toroid, you grab it, let me zoom all the way up. If you grab the toroid, and notice that my fingers go down and then up on the outside, and look at what direction my thumb goes as I go around the toroid. So it draws a circle like that. So that takes a little getting used to. Okay, let's talk now about the magnetic field in a solenoid. And a solenoid, this is very, very similar. A solenoid is just like a solenoid is just like a toroid, except that it's just stretched out like this. So imagine I've got like a a rectangle like this, and what I'm going to do is I'm going to wrap wire around it to make a coil. I'm going to make a coil of wire. So let's do it like this. Boom, boom, boom. See what I learned in college? I learned how to do this. Little integral signs they kind of look like, huh? Okay, and that's how you draw little wires in 3D going around a, this is really a cylinder. Okay, so let's have the current going like this. There's the current I. Well, what happens is it's very similar to a solenoid. I'm just going to draw the magnetic field and then we'll actually calculate it. What it does is it creates a magnetic field line on the inside, and then it kind of goes way out. It's way, 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 way out, and then it comes all the way around and comes back in like this. Then you have another field line that goes way out, and then, so what happens is that you get a magnetic field that's quite strong. Now I'm crossing magnetic field lines, and you really shouldn't do that, but I'm just trying to draw a sketch here. So what I'm trying to show is that in the inside of the solenoid, the magnetic field turns out to be very strong, very intense. This is basically an electromagnet. You know, you've heard of electromagnets. Well, solenoid is another word for electromagnet. And this is how we create very strong magnets that we can turn on and off. When there's no current flowing through here, there's no magnetic field. So it's like there's no magnet there. But then when I turn the current on, I get a very strong magnetic field. And it's magnets like these, solenoids like these, that like in your car, you know, you have locks, you know, the electric locks in a car where you flick a switch up and all the locks on every door goes up, you know, and then you push the button down and it locks all your doors. Well, the mechanism that does that is an electromagnet inside your car. You put it down, it has current flow through a wire, creates a magnetic field. That magnetic field can pull this thing down and lock your car. So this is used all the time, solenoids. Okay, and so let's use Ampere's law to figure out what the magnetic field is on the inside, on the outside. Okay, now what I'm going to do is take a look at the outside here, and what if I drew a loop like this? Well, first, actually, let me draw this in cross section and zoom in a little bit. Let's take this solenoid. Now the rectangle is just drawn like this so that you can, it just makes it easier to visualize the spiraling in three-dimensional space. But if this current is coming around like this, boom, it goes into the paper here, 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 and here. And then it comes out here, 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 here. Okay, so these show the wires coming out, and then of course then they go in, and then out, and then back into the paper, and so on. And so if I were to draw a loop like this, okay, well, what do you see in my Amperian loop? I mean, how much current is penetrating through the surface of this, through the surface area defined by this Amperian loop? Well, for every current in, I have a current coming out. And so that means there's no magnetic field. Now that's the Ampere's law way of looking at it. There is another way of looking at it. And this is, again, this is very idealized, okay? This is very, very, very idealized. If you have lots and lots and lots and lots of currents, and they're very, very, very close together, here's what happens. Let's take a look at this wire right here. It's going in to the board, so I grab the wire with my right hand, twist it around, and this creates a little magnetic field like this. little magnetic field like this, like this, like this. Okay, so you see how these create magnetic field lines that are going down on the outside. On the inside, the magnetic fields go up. You see that? See how the magnetic fields go up? These are just little wires creating little magnetic fields around them. But look in between the wires. Do you see the direction? They're in opposite directions. So they tend to cancel out. The magnetic fields between the wires cancel out. And what happens is you get a line of magnetic field that looks like this. So you might say, well, wait a minute. Shouldn't there be a line of magnetic field going down this way? Well, yeah. If this was just a sheet of charge, or I mean a sheet of current, yeah. But look over here. Look over here. These have little magnetic fields too, but they're coming out of the paper instead of in. So when I grab each wire with my right hand, I use that right hand rule. Let me get my right hand in the picture here. You grab the wire. My thumb is pointed up. These create little magnetic fields that go like this. So they're going opposite. So notice here, when I grab it, it goes up and down, up, 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 up. So inside the solenoid, these reinforce each other to go up like this. And so what happens is that I get a very intense magnetic field inside the solenoid. Now what about outside? Shouldn't these be going down? Well, yeah, but notice, hey, these currents are also creating magnetic fields out here. So let's take a look at this wire right here and grab the wire and just show it way out here. This, oh, look at that. You see outside here, this current coming out of the paper tends to create a magnetic field line in this direction, in this direction, in this direction. Now if you have zillions of these, what happens is this. The current created by the magnetic field created by the currents coming out of the paper cancels out the magnetic field of the currents going into the paper outside the solenoid. See, these guys are trying to create a magnetic field line that is going up like this. While these guys are trying to create, oh wait, I'm sorry. These guys here are trying to create magnetic field lines that are going down like this, right? These currents are trying to create magnetic fields that are going down, but these guys are creating magnetic field lines that are going up. And so what happens is that they cancel each other out here. So, and the same thing happens on the other side. So what happens in a solenoid is this. There's essentially, in a perfect solenoid, there's no B field out here. No B field out here, but there's a very intense magnetic field on the inside. Because both these currents and these currents are both creating magnetic fields that are reinforcing each other. Now, of course, in the real world, you get even with a coil like this, you would have a little bit of magnetic field out here, but not very strong, because the magnetic field lines are going to go way out and then come back in this way. So the magnetic field here, it's not zero, but it's very weak. It's very, very weak. And so we essentially say that in a perfect world, in an idealized world, it would be exactly equal to 0. Well, in an idealized world, what is the magnetic field inside there? Well, the way we find magnetic fields in a highly symmetric situation is we use Ampere's law. So I'm going to make an Amperian loop like this. Okay, and in this Amperian loop, I'm going to say it has a length of L from here to here. It's a rectangle. I didn't draw it very well, but it's a rectangle. And so we're going to just use dot ds, and we're going to sum them all these b dot ds's up, and that will be equal to mu naught times the I enclosed. Well, if I come, let's start right here and just go around like this. Go here to here, b is 0. Okay, so from here to here, we just say, hey, there's no magnetic field out there. Now from here to here, well, the magnetic field is 0, magnetic field is 0. Oh, but once I get in here, there is a magnetic field, right? But what's the direction of the magnetic field? Well, it's perpendicular to my ds. Here's a little ds, here's a little ds. See my little ds is there? Well, the ds is perpendicular to the magnetic field inside the solenoid. And I'm taking the dot product of them. So even in the part of this length where I'm inside the solenoid, the dot product of b dot ds gives me 0. So it's really only this from here to here that gives me anything that isn't 0, because from here to here it's 0. So 0, 0, 0, but from here, there we go. So what is that? Well, that's B. That's what we want to know, is what is the magnetic field inside that solenoid. Now, what is ds in there? Well, it's L, right? And then this is going to be equal to mu naught times I enclosed, right? I enclosed. Well, how much current is enclosed there? Well, we have to count them. Like, well, here I have maybe one, two loops. But I mean, I want to do this in general. So what I'm going to do is I'm going to multiply this times the I enclosed. I'm going to say I enclosed is equal to the number of loops that are enclosed by this, so 1, 2 times I. So it's the number of loops that are, now this n is the, oh, I'm off screen, I'm sorry. The enclosed current, the current that's inside is the number of loops that are inside my Amperian loop. So this is inside the Amperian loop times I. Okay, so B is equal to mu naught times N, okay, the number of loops that are inside there times the current carried by the wire divided by L. And that's the magnitude of my magnetic field. B is equal to mu naught. Now I'm going to write it like this, N over L times I. This is the magnetic field, the strength of the magnetic field inside the solenoid. And we have a name for the number of loops per unit length. We call that N. N is the number of loops per unit length. So you quite often see this written as mu naught N I. So let's just write it like this. Mu naught N times I. This is the strength of the magnetic field inside a solenoid. And look, it depends on the current. It depends on the number of loops per unit length you have. But notice, and it depends on mu naught. But notice what it doesn't depend on. It doesn't depend on the radius of this solenoid or the surface area of the solenoid. No. It only depends on these three things, or these four things, if you consider the number of loops per unit length to be two separate things here. So this is, let me zoom all the way out so you can see the whole thing. This is how you use Ampere's law to figure out the strength of the magnetic field inside a solenoid. This is worth memorizing right here. This is, you'll see this a lot. And this has lots of applications in the real world. I mean, we use solenoids all the time. And notice that this magnetic field is uniform. It's a constant. It doesn't depend on R. It just depends on these things right here. It's a very interesting result. Okay, that's it.